And follow you, Tara.
Okay, so I hope everyone can hear me. I'm gonna start my screen. Can you see my screen? Okay, great. So yeah, I'm Tara, and I thought I will take the opportunity today to talk about a paper that's slightly different from usual. So it has a geotechnical engineering background, and since I'm like my studies is focused on geotechnics, I thought I will pick a machine learning related paper that's based on that. So the paper is called Deep Learning Based Pixel Level Rock Fragment Recognition During Tunnel Excavation using Instant Segmentation Model. And the authors of the papers are all from China, and most of them are from the Institute of Technology in Harbin. So first, I wanted to talk a bit about the background of the paper. So they in this paper, they wanted to find a method to assess the rock fragments during tunneling. So basically, during tunneling, you use this big machinery called a tunnel boring machine. And I don't know if all of you are familiar with it, but it's basically a very large machinery that has the diameter of the tunnel, and it excavates basically the tunnel. It has this big big thing at the tip, and it's excavating the rock in order to bore the tunnel. And it also installs like the panel at the same time, and it transports the excavated material on a conveyor belt. And basically during those operations, you have to adjust the speed of the tunnel boring machine to ensure safety. And usually how this is done is by a method like by eye, just by observing by eye, to see like how large the rock fragments are and see their morphological features. However, as you can tell, this method can lack in like accuracy, and like it's not very reliable basically. Another method that you could do is use a sieving technique. So in the sieving technique, you use like your rock fragments or like, for instance, sand, and then you use those sieves, and you basically have sieves that vary in sizes. So they go from large to smaller, and basically the bigger fragments get captured in the sieves that have the larger diameters, and the smaller fragments get down to the smaller sieve sizes. And you can produce this sketch that I've drawn here on the right, which is called a particle size distribution, and that you can use to also probably like control the speed of your tunnel boring machine. But as you can tell, this cannot be done in real time, as it's quite time consuming. Maybe now you might ask, you could also use a structural health monitoring system that's also installed in the tunnel. But with the tunnel boring machine, that makes a lot of vibrations. This monitoring technique is also, it will get disturbed a lot, basically, and you cannot use any measurements from it, as it will give you false results. It will say, oh yeah, the tunnel is close to collapse because of the vibrations. So you cannot use none of these techniques, and the authors came up with this technique, the method that they're explaining in this paper. So basically, what they want to use cameras in real time to capture the rock fragments. So this method can then be like a low-cost method, as those cameras are quite cheap to install, and this method can work continuously. So in their model, they proposed 2 subnetworks. One is object detection, so the detection of the rock fragments, and one is the semantic segmentation. And I will talk about them more in detail. So during the semantic segmentation, they use a U-Net. A U-Net is a method that I think was developed in Germany, and they have, so basically instead of having to have a lot of pictures to train the model, you can have less pictures, and the format that they then use is, I think, 512 by 512. So they make the picture smaller, the whole picture that was of a resolution of 4096 by 3072. And with this method, they are able to train the model with having like less pictures, basically. So downsampling stages use the structures of the object detection network to share the exact features of the rock fragments, and upsampling stages employ skip connection and self-attention modules to accomplish binary segmentation each detected bounding box. So for their method, they use 50 original pictures with the resolution that I already said, and they use 35 for the training and 15 for the testing of their methods. Their method was able to detect very small fragments that were missed during the initial labeling process. Like they labeled everything initially just to get their ground truth. And they were also able to identify extremely large pieces. And then afterwards, they had their particle size distribution, and their particle size distribution fitted well with the ground truth particle size distribution. So I'm now going to go like step by step through the paper. Here at the top, you can see a schematic of their method. And so to their methodology. So the overall framework, first they proposed image pre-processing for eliminating the pure background, black background, and enhancing the contrast of the rock fragments. Then they used the instance segmentation to recognize the individual regions for each rock fragment. And lastly, the image post-processing to assemble and refine the global recognition result and obtain the distribution curves of the rock fragments. So in the first stage, they used a homomorphic filter. This is a filter, sorry, I skipped the page. So this is a filter that helps to improve the high frequencies and helps to remove the low frequencies. So if you have an image, you can imagine like a gray and black image. You can imagine you have maybe some black contours, and you want to enhance those sharp edges and get rid of all the blurriness that's inside the image. That's the aim of this method. So in this method, you have two different terms. So in equation 1, you have your original image, and then you have an illumination component, and you have a reflective component. The accent Y here is the width and the height coordinates of the image. And yeah, like the original grayscale image, you have the high frequency reflectance components, the second one, and you have the low frequency illumination, which is this first term. Then to this, you're gonna apply the Fourier transformation to the logarithmic form of this. And this whole method, it's called a high pass filter in the log intensity Fourier domain. So basically here in this equation number 3, HUV is your high pass filter. So if gamma H is larger than 1, it amplifies the high frequency components, which is what you wanted to do. And if gamma L is smaller than 1, you suppress the low frequency components. And then you also have some parameters that define the cutoff distance, basically. And to this term, you're gonna apply the inverse Fourier transform. And afterwards here, you're gonna get the reconstructed image after the filtering. After applying this method, they also applied a grayscale histogram. So in this grayscale histogram, what you have probably at the beginning, it's like a low contrast image. And what you want is you want to equalize the image colors. So in a gray, 55 is white. So you're gonna equalize all those colors in your image. So initially you might have an image where the histogram looks similar to what's here in blue. And then you're gonna stretch everything out until you have your equalized image here that I plotted here in yellow, and like then your color scales are much better distributed, basically. So
Sorry, I have
Go ahead, man.
sorry, I had a quick question about the pre-processing, which maybe it's obvious, but why did they take the logarithm of sort of the image and then took the exponential for the Fourier transform? Because
I think what you cannot put it in this form if you're not using the logarithmic form. I think when you convert it to the logarithmic term, I think mathematically you still want those two to be separated. And I think like in mathematical expression, when you have this initial expression, you can end up with this one when you do.
but they don't use the split explicitly in 3, right? So that's why I was a bit confused why they have this two split between illumination and reflectance. But maybe it's just notation. Yeah, I don't know.
I think it's mathematical notations. I'm not really an expert in that. I think I saw some YouTube video that explains this quite nicely. Maybe I can send you the link to that later on.
All right. Okay.
But I'm not so much of an expert of this. If you're interested, I can share that with you.
One reason to do it would be either the numbers are very large or very small, and so you want to avoid numerical issues like massive variation in the illumination that you see. So the logarithm has a tendency to like squeeze things. So that's why we usually operate in the log space with probabilities, because if they're really small, then you can basically make them lower than the precision of floating point numbers on a computer if you multiply them. But if you're using log scale, then that doesn't happen. Maybe it's something along those lines. I don't know.
Yeah, probably.
I had one quick question.
Yeah.
Why do you think they do this grayscale histogram equalization? Why is it done?
So initially they say they have very dark images. So I guess like with their camera, they capture very black images. Like I think they say, I don't remember where it exactly says, but the original images are basically black and you cannot see too much. So from those very dark images, by doing this equalization, they will be better able to distinguish like the individual particles. I'm guessing like the image that's shown on this one in this page is already equalized, so you can just imagine this one even darker, and I guess it's very difficult then to even like see like the edges or even the pieces in those images.
Okay, that makes sense.
So yeah, then they have basically two subnetworks. One is for the object detection and one is for the semantic segmentation. So the top one here on this schematic is the object detection one, and the bottom one is the semantic segmentation one. And in this one, they're basically feeding in the images that have a resolution of 512 by 512 pixels. So from the bigger size image, they obtain a lot of smaller ones, and they sliding those images with an overlap of 256 pixels to not miss any like pieces in between, basically, that might be cut off. And then, yeah, they use those two subnetworks. So in the first one, in the object detection subnetwork, they have a series of rectangular bounding boxes where they generate like those bounding boxes to distinguish between each of the rock fragments. So here at the top, you can see all those bounding boxes in green, and each bounding boxes has one rock fragment inside of it. And then for the semantic segmentation, they feed this in, and they have a pixel level rock fragments in each bounding box. So they look at each bounding box and they detect the fragments that are inside each of those bounding boxes, basically. So they are able to distinguish various rock fragments with a wide diversity of geometry, as you can say, and also different sizes in those bounding boxes. So more in detail to the object detection subnetwork. So they use a modified single shot detector, and all those they have these individual layers where they apply, like they have a feature map, and yeah, they have the layers that go from D1 to D7. And at each stage, they have a series of convolutional, like they use a batch normalization, a ReLU, and a max pooling layers within them. So basically, for instance, a max pooling layer is when you have your feature map here, and then you're gonna say like which one is the largest feature, like for a certain segment. So you're gonna, if this is like 2 by 2, you're gonna end up with this, basically. Yeah, and then ReLU, I'm not gonna go too much into detail, but it stands for refined linear unit. And basically you're gonna see on this scale, which is very small because I didn't have much space there, like if you go more to the right, you have a new number that basically goes in. But if it's on the left, it will stay with the largest number, like either will be yours, or if it's 0 here, then it will stay 0. If you have, for instance, like -2, you will stay at 0. Yeah, so you have the feature maps from stage D3 to D5. And then you're also gonna identify prior anchors at stage D3 to D7. So in order to identify those anchors, they use a probability density function. So I'll go back to that figure here, which is their distribution, and they select the 97% coverage here. They divide this in 9 different sections, and then they select 10 different nodal values from each of the sections. So here's one nodal value at 39, 37, 67, and then they're gonna use them as Vmin and Vmax in stage D3 to D7. So basically for D3 here, the Vmin is 39 and the Vmax is 67, and so on. And you can see like the different stages shown here in the network here to identify all of their rectangular bounding boxes. Yeah, the anchors here are calculated like this. I was a bit unclear myself what they were exactly doing with the anchors, I have to admit. So afterwards, they came up with different width to height ratios from the anchors, which is 2x1, 1x2, 3x1, and 1x3. And I think they were saying somewhere that they were only using 4 or 5 different ones to speed up the process. I don't remember where it exactly says that. So afterwards, they also use a self-attention module. So if you think about the self-attention module, maybe you think about it more in terms of a natural language processing. So if you have a sentence and you have different words, you're going to compare each word with all the words and also itself. And in this case, you're just going to compare like each pixels with the surrounding pixels. Then they also applied a softmax operator. So that one is basically a probability distribution. So how probable it is for a pixel to belong to a certain class. Or if you have another example, if you have an image of like, I don't know, a horse, a chair, and a car, and you feed in the image of a chair, it will give you a probability. So they will have a probability of how likely it will be that your image belongs to that class, basically.
Sorry, quick question. And a class being, so there are, I think I heard somewhere 2 classes. So one being
Yes.
it is in a bounding box and one it isn't.
Yeah.
Okay.
Basically here it's just 2 classes. So yeah, then yeah, from all those steps, they were able to identify the anchors, and for each anchor they have this value of h, which is a tuple with 4 elements. So it contains the center coordinate, the width, the height. So yeah, 2 center coordinates and then the width of the box and the height of the box. And then you have the number of bounding boxes containing rock fragments. And then you have, yeah, a binary indicator, which is either 1 or 0, saying like contains a rock fragment or doesn't contain a rock fragment. So yeah, then, I mean, they also define the different parameters for their model. They have the minimum batch size, the momentum, and the learning rate that they defined for their model. So now I will go to the second subnetwork, which is the semantic segmentation subnetwork. So using the recognized bounding boxes from the first subnet, the input images of the object detection subnetwork, the individual rectangular regions can be regarded as input of the semantic network. Yeah, so basically they use that as their input. And yeah, they use the UNet, which is what I already explained. It's when you have images, the pixels that are 512 and by 512, when you like from a bigger image create a lot of smaller ones. And now they're gonna come to like their object detection. So I'm gonna go to this figure down here. So basically what they are doing here is they have different steps. and each step they have their bounding boxes, yeah, the consecutive vertices angle is less than 180 degrees, so they rotate it. They rotate this box, and at each rotation, it's aligned with one of the edges, basically. So it rotates clockwise rotation, and then you're gonna define a minimal external rectangle with those boxes, and these boxes then afterwards help to identify the major and minor axis of the rock fragment, and also you can then deduct the pixel, in terms of pixels, the length of the rock fragments to, for instance, create your distribution curves. So yeah, you basically go from left to right, you're gonna rotate those boxes, and every time you're gonna have one of the box edges here aligned with one of the edges of your fragment, and this way you're gonna identify those fragments. Yeah, here it's like explained. I think it's explained here, yeah, in more detail in this part. And you can see here just a schematic of how, oh yeah, so the original image here, to Peter's question, is very dark. You can see, you can like almost not see anything. And then you're gonna apply the homomorphic filtering. And with this filtering, you can see you can already distinguish slightly more. And then after the histogram equalization, you can, like, if you would label this, I guess by hand, you would be able to see the different rock fragments. And then, yeah, they label this by hand, which is their ground truth annotation. But they said when they were labeling it, they missed a lot of smaller pieces. So yeah, now to how they implemented their model. So their original data is from a tunnel called Wingling tunnel in China. And it had different like morphological features. It had marble, granite, and gneiss. I don't know what's gneiss, but yeah, probably you know, like most people know what's marble and granite. And then the rock fragments from those tunnels were collected and transported on the conveyor belts to the ground. Like I said, a tunnel boring machine, like the rock fragments from the face of the tunnel boring machine, get transported inside the tunnel boring machine on a conveyor belt. And yeah, they sampled those and they captured 50 rock fragment images, and their resolution was this. Then what I already explained, they applied this homomorphic filtering and the grayscale histogram equalizations, and then afterwards they labeled the rock fragments here by hand, and yeah, then they applied the two sub networks. So I'm going to skip this part, but yeah, now to their results. So they had 35 images that they used for the training of their models, and they were cut into 512 by 512 pixel batches with an overlap of 256. So they had a total of 5,775 sub-images from this to feed into their model. So you can see how much like your training images can increase by just using this method. So yeah, they said they also neglected a bunch of pictures that only had pure background. So they, at the end, they only used 5,185 sub-images that contained rock fragments. And of those, 4,700 were used for training, and 400 were used, about 400 were used for validation. Here at the bottom, you can see what they obtained. So this is the original image after the homomorphic filtering and the equalization. So that's the input picture, and they labeled this input picture, and you can see all the different rock fragments that they recognize. And then this is the predicted one with their model. And what they were saying is they could also identify smaller pieces that they were not originally able to identify using the labeling techniques. So for instance, here on the right, you can see that they only identified 3 pieces as ground truth, but then using their model, I mean, they missed this piece, but they were then able to identify 2 additional pieces that were in the image. As you can see, there's like a small piece here. I'm not sure why they missed it, but yeah. So afterwards, they reconstructed the whole images. So from those smaller segments of 512 by 512, they reconstructed the original image, and you can see all the individual particles that they were able to identify and the ones that they originally labeled. So they were saying that several small rock fragments are misidentified, reducing the precision of the object detection and recall, but the recall remains quite high. The object detection subnetworks achieves a high recognition, and the semantic segmentation network also has a high recall of object detection. Then for the instance segmentation results, they labeled rock fragments are generally identified well. The accuracy of manual labeling, some small rock fragments were missed when labeling, and the trained model can recognize those missing areas. And you can see also, like here, like it's a zoom in of one of those images. I don't know which one, but it's a zoom in of one. And you can see that they were able to identify a lot of different rock fragments of various sizes. So yeah, afterwards they assessed like how good their method was. I'm not going to go too much into detail here, but yeah, their identification was quite good, and they also compared it to the ground truth particle size distribution, where they used the pixel size instead of like millimeters for that. But you can easily convert if you know the scale. So they say that's not a problem. They say that their method is quite good as a proposed like real-time method, and much more reliable than having someone like just look visually at the rock fragments and say, oh, I think the machine really has to go at a slower pace or higher pace, for instance.
Hard. I remember you said that you saw, was this a paper that you saw some people present or no? The authors present or no?
So basically what I went to this conference, and I didn't see those authors present. I saw some other authors present something similar It was like a machinery that was used, I think, to measure the pressure on the tunnel, and with those measurements, they could use a deep learning machine to predict like the strength of the tunnel walls, I think it was. But the problem with that paper was it was only 2 pages long or 3 pages long, because this was a conference paper, and I found it was a bit too short. I could only speak about 10 minutes about it, and that would be it. I mean, that presentation was also only 10 minutes.
Yeah, I was just asking because I was wondering, like, these results seem really good, and I was wondering if they had used it in this project or not. Like, if they, after they were done, if they had given the model to the engineers that were making this tunnel in order to use it to make the tunnel.
I don't think
yeah.
it has been applied yet. I mean, this is now different authors. I wanted to find something like really similar as a paper, or like in a similar sense. And when I was looking for like TBM and deep learning, this was quite an interesting paper for me that showed up. So that's why I picked that one.
Yeah.
Yeah, I mean, here at the end is just a few nice images, like maybe I zoom in slightly, that they obtained in their model. Like they were using different parameters and comparing here. But I didn't go too much into detail in this section because it's very specific, and I'm not that much of an expert in that field. But they were basically discussing like with the different methods how good their results were.
Yeah, they identify like 5 different elements which they say compose their method, and they're just showing images for each of those different 5 methods. It's actually a little bit hard to tell the differences, but you can see, and they do highlight them with the circled parts. Like this is, these are artifacts that the model identifies that just aren't there.
Yeah.
I was actually thinking when I saw this, I can totally understand why they did an ablation study as a baseline to show that their model is good. But I was wondering if there was like a much simpler baseline they could have used to compare their model to, like, I don't know, something that literally just uses edge detection, like the classical version of edge detection, which is a predetermined filter that you can apply to an image to do segmentation, and how good that would be. But I think these results still, like, they're really good. So I think that's why they were like, yeah, we'll just use this ablation study to show the effectiveness of our method.
Yeah. I don't know too much about the different techniques that also exist to assess those. So yeah, that's I didn't really think about their method of how they assess this.
Sorry, I have a quick comment. I feel like for these.
Nay, if you're really faint.
Oh, hi. Hello.
Okay, there we go.
Okay, yeah, I was just a bit further away from my laptop. I was thinking, I feel like for this to be sort of very applicable in the real world, it would need to be applied to maybe 3D volumes. And so I'm thinking, like, did they mention anything being done, or are they working on sort of doing the same sort of research on 3D volumes?
They on the second page, which I kind of skipped, they were saying about different methods that were used in the past, and they were also using something about 3D like scanning. And I mean, 1 second.
Because there's lots of research at the moment, I think, on sort of 3D protein detections, also proteins in 3D images. So maybe that could be applied.
So yeah, they stated something about this first or second authors here. that that 3D shapes, that they use 3D shapes for tunnel lining. I didn't read this too much in detail, so I can't really say too much about it right now. But they definitely mention like different methods that rely on 3D, and I think at the end they also say something about their future work. Find it.
Nayev, why do you think that they need to apply it in 3D?
Well, because I think most of the images that I know nothing about tunneling, right? So take this with a grain of salt. But I feel like a lot of the images that they use sort of maybe some sort of like maybe sonar detection or something. So I feel like the images that they get from the ground are going to be these sort of 3D volumes of the ground. And I feel like they want to get more than just a 2D picture of the rocks.
Well,
they want to know more about sort of the size in sort of a three-dimensional.
I think it's okay because, you know, when you excavate, like everything that gets excavated at the front gets put on like a conveyor belt. So you're gonna end up with a lot of pieces maybe that were like more at the top or at the middle, or like distributed through this like whole space that's within the diameter that's been excavated. And all that material will be on that conveyor belt. And since it's like, even though it says, oh, it's quite fast or there's a lot of volume that's excavated in a day, still when you put it on the conveyor belt, you can kind of, I don't think the volume exceeds like as much as this high, but then when you take pictures, all the rocks will be like orientated in different orientation, and then when you take a lot of pictures along that, you're gonna probably end up with a good idea about how a piece in 3D would look like, I'm thinking.
All right, because I thought they would sort of maybe be halfway through a dig and then they would take an image, and then sort of they would dig a bit more and then they would take a 2D image, and then that's what they would apply this for. But okay, but yeah, what you said makes sense then. Yeah,
the way I understood this is like when you excavate, you have this like it's like rotating, and it has like teeth along it, and the material that gets excavated just slides through those teeth, I think, and then it lands on this conveyor belt, and they take images or want to take images of all the pieces that gets transported in real time along this conveyor belt. And from those images, you can maybe suddenly say, oh, now we're in a part where the pieces became suddenly much smaller than they were before. And maybe if they're much smaller, then you have to excavate at a slower rate because the tunnel might be less stable or something like that. So when identifying this, you might and monitoring continuously, you might pick that up by looking at that.
Yeah, that makes sense.
So yeah, you're not actually standing in the tunnel looking at the surface, because I don't think you can do that because the tunnel boring machine is right up against the wall, unless they move it backwards, which takes quite some time. I think maybe the machinery moves at maybe 1 or 2 meters per hour. Yes, I think some idea of a rate it might have, maybe up to 6 meters. But it's a quite slow pace. So if you want to move this massive machinery back, it's not really feasible, basically. But what I know is people can go like inside the machinery, like you can walk through it. Yeah, like probably some have like a diameter of like 6 meters if you think about the Eurotunnel, for instance. So yeah.
Cool. I think that if there are no more questions, then are there any more questions? Okay, cool. If there's no more questions, I'm gonna stop recording.